In this video, I will discuss power in the context of electricity and magnetism. So we know from introductory physics that power is defined, you can define it as the change in the energy over the change in time. Now, because we know that energy is conserved, we have the energy conservation principle. The change in the energy of the system is equal to the external work done plus Q. So if we make the assumption that we're not dealing with heat, in our cases, whether you do the change in the energy or work over delta T, it's going to give you the same thing. Now, I also want to mention we have seen by definition the change in the electrical potential energy divided by the charge Q will give us the change in potential. Now, I can use this, can say if the only thing that contributes to the change in energy, if I'm only dealing with the electrical potential energy, and then I have delta V over delta T, Q delta V over delta T, but I can rewrite this as delta V times, let me do this again, delta V times the charge over delta T. Now, if I assume that I'm working with a small time period and this is about small charge delta Q, then we know by definition delta Q over delta T is what we defined as the conventional current. Okay, I want to remind you this is the conventional current that has the units are amperes, but essentially it is coulombs over seconds. Okay, the units of this coulombs over seconds, or we most often use amperes. Now, okay, I want you to pay attention to, I have not made any assumptions about whether the material, the object, is ohmic or non-ohmic to arrive to this expression. So when you deal with circuits, for example, you can use and you should use what I just proved, delta V times I. Okay, I have used an equation that relates the change in the electrical potential energy with the charge and the change in potential, which is always valid. Okay, there is no case you will find that this is not correct. I have also made the assumption that Q is 0. I don't have any heat. Delta V times I is the way that I would like you to start when it's time to calculate the power. And this is why I say that. We know if you have an ohmic material, then you can say delta V equals IR for that ohmic object. And of course, then you can say, well, if this is true, then the power can be calculated as I squared times R. But I do want you to remember that not all materials are ohmic. Now, if you actually do, okay, let's say this is I and this is your delta V. If you do have an ohmic object, an object that's made from an ohmic material, yeah, you will find you do measurements, different delta V, what current you get, and you will find, of course, the slope of this to be your resistance if it is ohmic. Now, if it is not ohmic, you're gonna get something that maintains where the slope. Okay, let's see. You're gonna get a slope that is changing as you change the potential difference, or as you control the current. Now, my point is that this is applicable only when you have an object made from ohmic materials. This is something that you can use in more general cases. That's why I would like you to start with this. And if we're talking about an ohmic resistor, then go ahead and use delta V equals IR to find the power. But always start with this.